In this video, I'm going to find the instantaneous velocity at each of these points along the graph. And I'm going to show a few different ways how we can do it. So let's get into it. Starting with A. Now, one thing we notice about A, first of all, is the curve that it's along. And the fact that it's not actually a curve, it's a straight line. What this means is, well, we know that instantaneous velocity is the tangent line to a curve. But if you have a straight line, technically, this is already the tangent line, and so all we have to do is find the slope of this line. Now, how we could do that is, like usual with average velocity, is find nice points along the plot, and then use that to find the slope. So I'm going to pick two nice points. Nice points meaning they line up with the lines on the graph. So I'm going to take this point at 0 and 60, and this point at 0 and 2. So I'm going to draw it on this paper here. So point A. We have a point at 0, 60 and 2, 30 here. Now we can find the slope. I'll call it M, which is our Y. So this will be like 0.2 and 0.1. And we'll take y2 minus y1 over x2 minus x1, as usual. And so that's 30 minus 60 over 2 minus 0. And if you put that in, your slope equals minus 15. And therefore, our velocity at A is equal to minus 15 meters per second. If this is the positive direction for x. And, of course, I should put units here of meters per second. Sorry, meters. And then this should be seconds. So that's one way we can do it. The other way is if you know what the equation for this line is. And so I'm just going to tell you the equation that this line has the equation y equals negative 15x plus 60. So notice this is the same as this because that's the slope of this line. Now what we can do, actually to make this more accurate, this should be x equals negative 15t plus 60 because our x-axis is actually t and our y-axis is x. We could take the derivative of this equation with respect to time using our power rule. And so this is a constant, so if you take the derivative of a constant, it's equal to 0. Then we use our power rule here, so we bring the one exponent, this is t to the power of 1, that out front, and then subtract, which of course is t to the power of 0, which is 1. And you're left with 15, minus 15. So you get the same answer using both ways. And that's because, like I said, for a straight line, that line is equal to the tangent line. Okay, let's try B. B is also a straight line, and it's not changing along x. So you may already know what the answer to this will be, but let's work out the math. So again, I'm going to take this point, and now this will be P1 and this will be P2, and I'm going to take, this is 330, so we're going to go 30 minus 30, and we're moving from 2 to 3 seconds, so 3 minus 2. and this works out to 0. Because we're not moving along x at all. We're just sitting at the same point in space, 30 meters, for a second. So we're not moving. And if I were to take the derivative of this function, which is x equals 30, like I mentioned with constants, if you take the derivative of a constant, it's 0. And so you get 0 meters per second. Okay, so C, point C. Now this is similar to A. We can find nice points along the graph. And C is a nice point, as were A and B. I just chose different ones. But I'm going to use C in this one. So we have, this will be P1 now, and this will be P2 for this line. And let's find the slope like this. So we have our P2, which is 70, minus y1, so that's y2 minus y1, which is 30, divided by x2, which is 4, minus x1, which is 3. And so what we get is we get 40 over 1. And so our slope, which I'll write as our velocity because that's what it is, our instantaneous velocity at point C is 40 meters per second. Now, one thing as sort of a side note is that these have direction to them because I declared this as the positive direction and we got a negative slope here because we're going in the negative direction. So these positive and negative signs indicate there's a direction to these velocities and therefore it is a complete vector. So we have our magnitude, say 15, and then our direction of positive or negative. Okay, now, also if I took the derivative of this function too, it would be the same, but I won't do it for this one. Point D. Now this is where we need to do a little extra work because we are on a curve here. So if you knew the equation to this function, to this line here, this curve, then you could just use that and take the derivative. But for now, and I mean, I know the equation to this function and I'll do that later, but if we don't know, we gotta draw our own tangent line here and find the slope of that. So I'm gonna try to use my ruler here, find a good tangent line. Something like this. Oop. And you can cross, if you can find some, is that even working? If you can find some good points along here, then you can use those. So that's our tangent line, the line that only touches the curve at the point B. And now we can look along this line and see if we can see any nice points. So we can get close enough, like there's a nice point. Is there any other along here? We could take this point. It's going to be slightly inaccurate, which is why it's better to take derivatives. And if you have software that's good at finding tangent lines, then it would be more accurate. But doing it on paper like this can be inaccurate. But let's do it. So we have our P1 here and P2 now. So let's find the slope. So P2 is at 8.5 and 35. So y is 35. P1 is at a y equals 55 over 8.5 minus 5.5. And so what we get is that this is 20 divided by 3. Or, if I put that in my calculator to get a decimal, our velocity at point D, sorry, this should be negative 20 because 35 minus 55, we get about negative 6.67 meters per second. Now E, I'm just going to tell you right now, if you find the tangent line, it's going to be 0. It's going to be right along the 45, the x equals 45 here, and so E also equals 0, similar to B. And finally, we have our last point, F. So we can attempt to draw another tangent line. Something like this, I would think. This pen isn't very good. Something like that. Now I meant to draw this kind of through this point here. It lines up well enough. And then we could take this point or something like that. So again, we have our P1 and our P2. And we can find the slope of that line now. So F, I'm going to switch sides with this. So F, this is Y2 is, oh, now I need to see this. So Y2 is minus 10 minus 45 divided by, this is 12 minus 10. And so we get minus 10 minus 45 equals minus 55 over 2. So minus 55 over 2. Our velocity at F is equal to negative 27.5 meters per second. Perfect. Now, I told you earlier that I know the equation of this line. Let me put that aside. I know the equation of this line here, this curve, because I graphed this. So if I tell you what this equation is, if you know what it is, we can take the derivative of it, and therefore we could find D, E, and F by doing that. So I'm going to just give you this equation now, which is x equals negative t minus 8 cubed plus 45. And that's from here all the way down. So we want to find the derivative of this. So to do this first, let's expand it. And I'm not going to do all the steps. I'm just going to write it out for you. So you get that this expands out to negative t cubed plus 24 t squared minus 192t plus 467. That's what this equation expands out to if you multiply all if you multiply the cube through everything. So now we can find the derivative. So like usual, use our power rule. Bring the 3 down, you get negative 3t exponent minus 1 is 2, plus, bring the 2 down, 24 times 2 is 48t, then minus 192. And then the constant is 0. So now, this is our equation for the slope at any point along this curve. So all we have to do is plug in the t values and we can find our answer. And now this is the accurate way to do things. If you know the equation, it's going to be 100% accurate. With my tangent lines, it's sort of eyeballing it and it'll be slightly inaccurate. Okay, so let's plug in for d. T is equal to 6.5. So our velocity our instantaneous velocity at point D is equal to negative 3 times 6.5 squared plus 48 times 6.5 minus 192. And so our velocity at D, if I grab my calculator, 6.5 squared times negative 3 plus 45 or 48 times 6.5 minus 192. What we get is negative 6.75 meters per second. And note what I got was negative 6.67. And the difference is pretty close. I'm pretty happy with that actually. The difference is just, again, my inaccuracies in drawing the line with the right slope. But it's close. But 6.75, negative 6.75 is the correct answer. And so that's how you do problems like this, finding instantaneous velocity at these different points. If you know the functions, like if you have a straight line, you can easily find the function if you want and then take the derivative of it. But it's harder for these curves if you don't know the function. Then you have to resort to drawing the tangent lines, and you might lose a bit of accuracy if you do it that way. But that's how you do that problem. So thank you for watching.